Now, I say they affect the geometry. Some of you, if you're as old as I am, may have done geometry at school. And you've heard of Euclid, and you know that straight lines in a triangle add up to 180 degrees, or two right angles. You also know that if you were to do the nearest thing to straight lines on a sphere, you get a different answer. Imagine drawing a line from the North Pole down to the equator, and then round through 90 degrees and back up again. That's three right angles. So triangles on the surface of a sphere, or the nearest thing to triangles, they add up to more than 180, because the surface of the sphere is curved. And if you had a saddle shape curved the other way, you'd get the opposite effect. The triangles there would have points that, angles that added up to less than two right angles, less than 180. This is a feature of the geometry of a surface. Now, what we're talking about now is not the geometry of a surface, but the geometry of the whole of space. And what we're saying is, if the geometry of the whole of space was curved in this sort of way, then really big triangles thousands of millions of light years across, the angles would add up to a bit more than 180. And if it was bent the other way, they'd add up to a bit less. And if it was just flat, it'd add up to 180. It's not the universe being flat or spherical, it's the geometry of the universe being affected like this. And what the geometry of the universe depends on is how much matter there is. Matter makes it sort of go in the spherical direction, and how much energy there is, if you like, how fast the matter's moving and other things, that makes it go the other way. Now, I'm conscious that's a bit difficult. The visible universe seems to be uniform in all directions. So far as we can tell, it isn't that the universe is flat, but so far as we can tell, the geometry is flat. It's pretty close to Euclidean geometry, which means the energy density and the matter density are pretty finely balanced. Have you heard about dark matter and dark energy? Yes. This here, I'm jumping on a bit, is a graph of the way the universe might have expanded with different amounts of stuff in it. You see this orange curve? That's what would have happened if, on a certain scale, there was 5 times as much stuff as is needed to make it flat. It would have started expanding, and just like gravity slows things down, it would have got to a bit just past where we are now, and then it would have contracted again. The matter would have pulled it together, and the universe would, in the end, contract to nothing. So it goes up and back again, and the geometry would actually be this spherical thing. Now, look at the green curve. That would be what would happen if there was just enough matter balanced with just enough energy, sort of going just fast enough. It would be like throwing up a stone that was just going to leave the Earth. It's slowing down a bit, it never quite comes to a halt. And the geometry would then be flat. It would go on expanding, but always slowing down. Now, in fact, there isn't that much matter. And if it was only 0.3 of that one bit, the blue curve would be followed, and the universe would go on flying apart forever. Okay? But what we actually think is that there is not only matter, but some stuff called dark energy, which has 2 opposite effects. These 2 add up to 1, so the geometry is flat. But blow me, the dark energy has a pushing effect rather than a pulling effect in its gravity. So the universe not only goes on expanding, it actually goes on expanding faster and faster and faster. That's the curve we're actually in. Now, that curve says there's that much matter and that much energy. And let me talk about the matter first of all. 30%, the 0.3, is matter, but actually most of that matter is not ordinary matter, it's dark matter. So, what we're saying is 70% of the stuff in the universe which controls the geometry is energy, 30% is matter, and most of that matter is actually dark matter. Hold your hats, we're getting there. Let's talk about the dark matter first of all. What's the evidence for dark matter? Matter that has gravity, but we can't see it. Well, the evidence for this has been accumulating for 50 years or more. For example, you look at clusters of galaxies, and they move around each other, just like planets move around the sun, the galaxies move around each other in orbits by gravity, okay? And you can guess how heavy a galaxy ought to be, because you count the stars roughly, or estimate how many stars there are. You know roughly how heavy a star is. You can guess how heavy a galaxy is. It doesn't work. The galaxies are moving too fast. They must have more mass somewhere to hold them in. The same is true of actual stars in a galaxy. They are going around in orbits on this big disk in the galaxy. They're being held in by gravity. But you measure the speeds, they're going too fast. There ain't enough mass in the galaxy, if you count the stars, to keep the stars going in a circle. There's something like 5 or 10 times more mass somewhere that's making the stars go in circles. I'm going to talk about the Wilkinson microwave anisotropy probe, but that has given evidence of the overall geometry of the universe. There must be dark matter, more matter than we can see. But finally, we now have direct experimental evidence that dark matter exists. This picture here is only about 2 weeks old. And what happens is this, that matter has an effect on light, it bends it. And they've now been able to look at patches of the sky and say, look, we can actually work out how much dark matter there must be from the lensing effect. And that is actually a sort of plot. The bright bits are where there's lots of dark matter, and the blue bits are much less. But we can actually begin now to plot out where the dark matter is in the universe. There is good evidence for dark matter. Dark in the sense, not that it's black, in the sense that it doesn't seem to reflect light or emit light or interact in any other way. It doesn't do anything except it's got gravity. We haven't got a clue what it is. Exciting, isn't it? Now, the other thing is dark energy. Now, the most extraordinary discovery in 1995 from these type 1a supernovae is that the universe is not only expanding, the expansion is accelerating. Nobody expected that. Everybody expected that the universe would be expanding. But to find that the universe expansion is actually getting faster was a complete and utter shock. And it was these measurements of type 1a supernovae that demonstrated that fact, and they've been confirmed in the 15 years following. So the observations of the type 1a supernovae show that the expansion of the universe is accelerating, and the only way you can get that is for there to be dark energy. I'll come back to that too. But actually it solves another problem. Here's a little bit of that graph that I showed you. These different things. That's lots of matter, that's enough matter but no energy, that's dark matter but not enough, and this is the actual one. And you see that they're all expanding at the same rate now, but if you extrapolate them backwards, it gives you different ages for the universe, okay? You don't get the right age by just drawing a straight line. You have to work out what the universe has been doing. Now, if you include the dark energy, it takes you back a little bit further. And that solves a problem, because it seemed as though there were things in the universe that were older than the universe. If you say the universe is about 10,000 million years old, and this star is about 12,000 million years old, that's the problem. How can a star be older than the universe? This red curve goes back a little bit further, and the problem's gone away. So it's another piece of evidence for this reality of this dark energy. You put all these things together, and we now have what's called the standard cosmological model. Lambda, cold. I realise that this computer isn't quite producing what we should have struck with the alphabet. I won't change it now. That's supposed to be a Greek L there. Lambda, cold, dark matter. These are the numbers. The age of the universe is 13,700 million years. That's when the Big Bang was. The Hubble constant, that's how fast it's expanding, is 70 kilometers per second per megaparsec. A megaparsec is a few million light years. It's a useful measurement. So that's how fast distant galaxies are going. On the scale of 1, ordinary matter is about 4%, dark matter is about 23%, dark energy is about 73%, and it adds up to pretty precisely 1. There are a few more things as well that make up the standard cosmological model, but these are the fundamental ones. And what I'm saying is that we now think that these numbers are right to about 1%. I could not have said that 10 years ago. The numbers were very much less precise, but there's reasonable confidence now that these things are right to about 1%. In other words, we know the age of the universe to within the order of 100 billion years, which is pretty remarkable, I think. Now, there are some quite remarkable unexplained coincidences about this model. Things we don't understand, but which seem to be necessary for life. And I've picked out 4 of them. The initial rate of the expansion, how big the bang was, if you like, how fast it started off, seems to have been astonishingly finely tuned. Secondly, this cosmic microwave background radiation, actually, I said it's very uniform. It's uniform to a few parts in 100,000, very uniform. But there are tiny fluctuations which actually are critically important, and they're just about the right size. Thirdly, why is there more matter than antimatter in the universe? The universe is virtually all matter. But the laws of physics are symmetrical between matter and antimatter. Sometime, right back in the beginning, there was a tiny fraction, about 1 part in a billion, more matter particles than antimatter particles. No one knows why. And finally, this cosmological constant, or the dark energy, is very, very small. I'll explain why, but it's just right for life. These are 4 things which are important, necessary for life, but totally unexplained. And I want to try and explain at least what they are, and not to explain how they... This, I think, is a rather remarkable graph. It turns out that if the geometry is about 1 now, it needs to have been very, very precisely 1 near the beginning. Any deviation from the balance between matter and energy right at the beginning gets expanded incredibly fast. And here is a number worked out at 1 nanosecond after the Big Bang. And I may say we think we know the physics pretty well down to 1 nanosecond. It gets a bit earlier, we don't know what's going on, but back to that time we're pretty sure. So, according to the calculated rate of expansion, that's how much matter you needed. 44722259172187287284016.0 grams per cc. Okay? Now imagine we made that 0.2 instead of 0. Then by now the universe would have collapsed again. Isn't that incredible? And if we made it a little bit smaller, it would be expanding much faster. So, quite astonishing. This very, very precise rate of expansion. If you go even further back, it gets even more finely tuned, ridiculous amounts. I've only gone far enough back where we think we know the physics. So, for some reason, the Big Bang banged at a very, very precise rate. Now, second thing is the cosmic microwave background radiation, or this reveals how uniform the universe was round about 300,000 or 400,000 years after the Big Bang. Here is a sort of picture. If you imagine you were looking from the outside at this radiation coming out, the red bits are slightly more intense and the blue bits are slightly less intense, and they actually are very small. They're parts in 100,000, less than 1/100th of 1%. So it's very, very uniform. But what they reveal are very small variations in temperature, which correspond to very small variations in density. Here is a more conventional plot, where in fact this is like the whole night sky. Every point that you can see is plotted on this graph. Do you follow me? Sort of imagine that wrapped right around the sphere. That's the whole sky showing the cosmic microwave background radiation as observed by WMAP. A huge amount of information here, but the relevant point I want to make now is that these variations are just about the right size. If they were much bigger, they would correspond to density variations and where gravity would have formed black holes and everything would have collapsed far too quickly. If they were much smaller variations, there wouldn't have been enough gravity to form anything, and planets and stars and galaxies would never have formed. In other words, people knew in advance, before they made these observations, that they knew they needed to find variations of the order of a few parts in 100,000. And they found them. If they hadn't found them, the theory would have been a mess. So it's absolutely crucial that these variations existed at this short time after the Big Bang. But nobody knows why they're that big. If they weren't that big, within a factor of 2 or something, then either things would have collapsed far too soon, or else they would never have collapsed to form stars and galaxies at all. Now, third thing. Here is this sort of a diagram of the Big Bang. So we're about here. Back here is where the universe was like the surface of the sun and was emitting what's now the cosmic microwave background. This is where the elements were being formed, quarks and protons and whatnot. But going right back here, and this is now a tiny, tiny fraction of a second, there was an incredibly rapid expansion, people think. Now, I'll come back to that. The thing I want to